everyone. So today we're going to be talking about volumes of revolution using the disk method. At the beginning of this video, I'm just going to kind of talk through what's going on here and build the formulas that we're going to need to find each of these volumes. If you already know the formulas and you're just looking for a couple of examples, feel free to fast forward through this part. So here we're looking at a graph of, let's say, f of x, bounded by x equals a, x equals b, and the x-axis. We've talked about in a previous video how to find the area of this two-dimensional region. I'll link to that in the comment section below. Today, what we're going to be talking about is taking this two-dimensional area and revolving it around the x-axis. So you're imagining this 2D shape coming up off the page at you, down and around the bottom, back around. It's going to form some kind of 3D shape that looks like this one over here on the right. Now, in order to figure out what the volume of this shape might be, I want to start by looking at maybe just one cross section of that shape. So maybe I'll look at this x value here, and if I draw a little line to the curve f of x, I know that the height of this section of the curve is f of whatever this x value may be. Maybe it's c. What I want to imagine is this little line, like a string almost, again, coming out at the page, down around the bottom and around the back. And that's going to form a nice little circular cross-sectional area of this 3D shape. If I wanted to find the area of just this specific circle, the area of this specific circle would be pi times the radius of the circle squared. Well, if the x value here is c, and I'm just drawing a circle centered at that axis of rotation, the x-axis, this distance is my radius. So that would really just be f of c. So pi f of c squared would give me the area of this circle. But I don't want the area of just one circle. What I really want to imagine is a whole bunch of these circles being drawn. And I would like to sum up the area of all of these circles to get the volume of this region. I can generalize this formula now to help me find that volume. I can look at the integral from x equals a to x equals b, so I can essentially sum up all of the areas of these circles. So pi r squared represents the area of the circle. Since pi is a constant, I can pull that out. And r is the radius of any circle between x equals a and x equals b in terms of x. If this is the curve f of x, all of my radii are going to start at the x-axis and end on that curve f of x. So I can represent all of these radii as just plain old f of x. So if I plug in f of x for r and square it, if I were to calculate that integral, that would give me the volume of this three-dimensional shape. We won't always be revolving around the x-axis. We can really revolve around any line. We'll focus today on revolving around horizontal lines and vertical lines. Some notes and formulas that we want to keep in mind moving forward. If our axis of rotation is horizontal, our radius will always be written in terms of x and will integrate in respect to x. Those bounds, a and b, will also be x values. The furthest most left x value of the bounded region and the furthest most right x value of the bounded region. If our axis of rotation is vertical, our capital R, our radius, will be written in terms of y, will integrate in respect to y, and these a and b values will actually be y values as opposed to x values. R will always represent the distance from the axis of rotation to the furthest side of the bounded region. And we just need to keep in mind that this method only works when the entire bounded region is touching your axis of rotation. If there's any space at all between the axis of rotation and the region that you're rotating, we cannot use the disk method. We'll have to use something else. Let's look at a few examples. So this first example I'm going to do in two ways, and then I'm going to use a regular volume formula to kind of verify that the integration formula we're using is really doing the trick. The first thing I want to do here is sketch the region that I'm rotating so that I can get an idea of whether or not I'm rotating around a horizontal or vertical axis. Are my bounds going to be x or y values? How do I need to write r? What variable do I need to integrate in respect to? In order to figure all of that out, I'm going to need a picture. We know that the line negative 2x plus 4 has a y-intercept of positive 4 and will pass through the x-axis at x equals 2. So here's my line, and I want to find the volume of the region enclosed by this line, x equals 0, and y equals 0. So we're looking for this triangle rotated around the x-axis. Since I'm rotating around the x-axis, that's a horizontal axis of rotation, so I need to use the formula v equals pi times the integral from a to b of r squared dx. A and b will be x values, r will be written in terms of x, and I'll integrate in respect to x. The bounds of my integral are going to be the furthest most left x value of my bounded region and the furthest most right x value of my bounded region. In this case, that furthest most left value is going to be right at x equals 0, and the furthest most right value will be x equals 2. So at this point, I have pi times the integral from 0 to 2, and now I need to figure out what r is. Capital R will always be the distance from the axis of rotation to the farthest side of the bounded region. No matter where I draw in this radius, it's always going to be the distance from the x-axis to the line. In this case, that's not always going to be the case, but this one specifically, that's the way that it's looking. That means that I can write capital R as the equation of that line, negative 2x plus 4. Any x value that I plug in between 0 and 2, when I plug it in, I'll get the distance from the x-axis to this line, which is what I need to represent for r. So when I plug that in, I'm going to have negative 2x plus 4 squared dx. A lot of these will be pretty easy to integrate by hand, but you can also stick them right in the calculator. The focus of this video is not integrating and plugging in values, so I am just going to give the answers for each of these. This first one, when you integrate and plug in, you end up with 32 pi over 3. Now, if I think about what this shape would actually look like if I were to revolve it around the x-axis, this would end up being a cone. So what I want to do is calculate the volume of that cone using our basic cone formula so we can kind of verify that we did in fact find this correctly. So if this is my cone, right, this would end up being somewhere over here. Sorry to draw over this old work, but it is what it is. All right, so that means, again, here's the radius of my cone. So my radius is 4, and then the height of this cone would be 2. If I work this out, 16 times 2, that's 32 pi over 3. Same thing, same answer, different way. Obviously, our shapes aren't always going to be so nice, something that we could use a regular volume for. For the most part, they're going to be something that you can't use this regular volume for. Part B asks us to take this same region and now rotate it about the y-axis as opposed to the x-axis. So again, I'm going to start by drawing out this graph. This line is still going to cross the y-axis at 4, the x-axis at 2. But in this instance, as opposed to rotating around the x-axis, I'm rotating around this y-axis. So now I'm imagining all of my shapes going vertically around this y-axis. For this one, since my axis of rotation is vertical, I want to use the formula v equals pi times the integral from a to b of r squared dy. So now capital R is going to be written in terms of y, and my a and b values are going to be y values. My a and b values are going to be the lowest y value of the bounded region and the highest y value of the bounded region. So if this triangle is still my bounded region, the lowest y value is down here, that's 0. And the highest y value of this region is up here, that's 4. So those bounds have changed slightly since I'm rotating around a different axis. R is still going to be found by calculating the distance from the axis of rotation to the farthest side of my bounded region. No matter where I draw in these R's, they are always the distance, again, just in this case, from the y-axis to this line. But since I'm calculating the y in this horizontal direction, I have to rewrite this line. So before we said the line was y equals 2x plus 4, but since these radii are now being calculated as x distances, right? They're these horizontal distances, I have to solve for x instead. When I solve for x here, I get y minus 4 over 2. So that means the distance from the y-axis to any point on this line can be represented as y minus 4 over negative 2. Whatever y value I plug in, I'll get the distance from here to here, from here to here, etc. So I can plug in y minus 4 over negative 2 for capital R, the radius of each of these little circles, square it, and integrate in respect to y. When we integrate here, we get 16 pi over 3. If I were to think about this in the same way I thought about this other problem in terms of a cone, I would have the rest of my cone somewhere over here. So again, my radius, if this is the top of my cone, or really the bottom of it, my radius is going to be 2. And in this distance, the height of the cone is 4. If I work that out, I still get 16 pi over 3. So again, I know that I've calculated this volume correctly. Let's look at a more complicated example where I'm not going to be able to verify with one of these basic volume formulas that I already know. Number 2, we want to find the volume if the region enclosed by y equals the cube root of x, y equals 0, and x equals 8 is rotated about the x-axis. Same idea as before, I need to start by drawing a picture so I have an idea of what my region looks like, and so that I can figure out the bounds of my integral and the radius of each of the circles. I know that the cube root of x looks something like this. This is, again, just a rough sketch. X equals 8 will be a vertical line. I'll stick it over here. And I'm also bounded by y equals 0, which is really just the x-axis. So it's this region in here that I am rotating around the x-axis. When I take this region and rotate it around the x-axis, this is kind of the general shape that you're going to get. So I wanted to include this at least in this one other example so you get an idea of what these 3D shapes really look like. Since I am rotating around this x-axis, I know I'm going to use the formula v equals pi times the integral from a to b of capital R squared dx. In this instance, since I'm integrating in respect to x, since it's a horizontal axis of rotation, my a and b values are going to be x values. It has to be the furthest most x value of my bounded region, which in this case is 0, and the furthest most right x value of the bounded region, which in this case is 8. Each of the radii that I can draw in here, again, are the distance from the axis of rotation to the farthest side of the bounded region. In this instance, no matter where I draw any of these lines from the axis of rotation to the farthest side of the bounded region, they are all starting at the x-axis and ending at y equals the cube root of x, which means I can represent capital R just as the cube root of x, because any value that I plug in for x, the distance will be just this cube root of x y value. So if I plug that in, I have the cube root of x squared dx. When I integrate, I get 96 pi over 5. Let's look at the same region, but rotate it around a different axis. So for part B, I'm going to take this same region, bounded again by cube root x, x equals 8, and the x-axis. But this time, I'm going to take this region and I'm going to rotate it around the line x equals 8. So now you're imagining each of these pieces, so maybe a piece in here, rotating around horizontally in this fashion. And you'll get like a little dome shape that's sitting on top of the x-axis. Since I'll be rotating around a vertical line, the formula I need for this one is pi times the integral from a to b of r squared dy, where capital R is going to be in terms of y, and my a and b values are going to be y values. These bounds on the integral have to be the lowest y value of the bounded region to the highest y value of the bounded region. If I know that this is the line x equals 8 and this point lies on the cube root of x, I know that this is the point 8 cube root 8 or 8, 2, which means the bounds on this graph, the bounds on this integral will be from 0 to 2. Now, when I figure out capital R again is always the distance from the axis of rotation to the farthest side of the bounded region. When I draw any of these R's, in this case, it will be the distance from the line x equals 8 to the curve cube root x. So I need a way to represent that in terms of y, since I'm integrating in respect to y, and these are horizontal distances. I know the distance from the y-axis to this red line is always 8, since this is the line x equals 8. I also know that the distance from the y-axis to this curve will always be whatever this formula is in terms of y. So if I solve for x here, that would be x equals y cubed. So this distance from the y-axis to this blue curve, depending on what y value I choose to plug in, will be the distance y cubed. Neither of these represents r. R is the distance from this vertical line to the curve. So I need to take this 8 distance and take the y cubed distance away. This means that I can represent capital R as 8 minus y cubed. So when I plug in here, capital R is 8 minus y cubed squared. I need to square that radius, dy. When I solve out this integral, I end up with 576 pi over 7. Let's look at one last example. Number 3, we want to find the volume if the region in the first quadrant, enclosed by y equals x squared, the y-axis and y equals 9, is first rotated about the y-axis. So again, I have to start with the picture. Since I'm only worried about the first quadrant, I'm just going to draw x squared when x is greater than 0. I also need the line y equals 9. So the region that I'm focused on is this region bounded by x squared, y equals 9, and the y-axis. So this piece in here. For part A, I'm rotating around the y-axis. So since my axis of rotation is vertical, I have to integrate in respect to y. Capital R will be written in terms of y, and my bounds will be y values. My bounds that are y values have to be the lowest y value of the bounded region to the biggest or highest y value of my bounded region. So in this case, that will be pi times the integral from 0 to 9. When I figure out r, again, r is always the distance from the y-axis to the curve y equals x squared. Any radii that I draw in from the y-axis to the farthest side of the curve are always going to be this distance from the y-axis to y equals x squared. It'll be helpful here to rewrite y so that it's an x equals. So that means x is going to be the square root of y, and any distance from the y-axis to this point on the curve will be rad y. So capital R is rad y, and if I plug that in, I have the square root of y squared dy. When we calculate this integral, we get 81 pi over 2. Let's look at one last setup. So in this example, we're taking the same region, but we're rotating it now around the line y equals 9. Each of my radii here will be the distance again from the axis of rotation to the farthest side of the bounded region. So each of these little yellow arrows represent different radii in this bounded region. Since I'm rotating around a horizontal axis, the formula I need is pi times the integral from a to b of r squared dx. My bounds in this case need to be x values, so I'm looking for the furthest left x value to the furthest right x value of my bounded region. If this is the line y equals 9, I know that x has to be 3, right? 3 squared would give me 9. So the bounds that I need here are going to be 0 to 3, x value to x value. Capital R, we had said, is the distance from the axis of rotation to this curve. I know the distance from my axis of rotation to the x-axis will just always be 9. That's not my radius. My radius would have to be this red line, and then I would need to subtract the distance from the x-axis to the parabola in order to get just those yellow arrows in between. I know any distance from the x-axis to the parabola can be written as x squared. So that means these radii between all of these red lines and then these little blue ones has to be the red minus the blue. So capital R in this case must be 9 minus x squared. If I plug that into my formula down here, now I have 9 minus x squared squared dx. If I calculate this volume, I get 108 pi over 3. That's it for volumes using the disk method. I hope this video was helpful. If you have any questions or comments, feel free to leave them below. Have a great day.